Greetings. Welcome to the homework exercise video that corresponds to the video lecture, Lecture 1.2, entitled Phases and Classification of Matter in the General Chemistry series presented by the Evidence Reasons Academy. You should be able to find a link to the corresponding lecture video, Lecture 1.2, in the video description. The material covered in this video is almost verbatim from the OpenStax General Chemistry book 2E and is reproduced here in this video under a Creative Commons License 4.0 as detailed in the video description. With that, let's dive into the homework exercises for section 1.2. And I'm going to do the odd numbered ones for the phases and classification of matter. And there are several of these exercises. So, question 9. What properties distinguish solids from liquids, liquids from gases, solids from gases? Solids maintain their form. Liquids can adopt the shape of the container. Liquids generally approximately occupy the same volume independent of pressure, whereas gases, the amount of gas in a volume is related to the pressure. And the difference between solids from gases, gases adopt the shape of the container. So now those are my answers. Let's look at the answer key. I have the answer key here. Liquids, okay, so the answer is liquids can change their shape, their flow, solids can't. Gases can undergo large volume changes as pressure changes. Liquids do not. Gases flow and change volume, solids do not. Okay, so my choice of words was different, but I think I got it mostly right. So now question 11. How does a homogeneous mixture differ from a pure substance? How are they similar? A homogeneous mixture differs from a pure substance in that you can change the proportion of the parts that make up the mixture, whereas a pure substance, you can't really change the proportion of whatever makes it up. It's always the same. You can't change the proportion of things that make up a pure substance. How are they similar? My guess is that they are from one point to another, either in a mixture or a pure substance. One point, if you sample one point of a homogeneous mixture or a pure substance, it'll be the same as any other point. So let's look at the answer key. The mixture can have a variety of compositions. A pure substance has a definite composition. So that's a better way of phrasing it. A pure substance has a definite composition. Both have the same composition from point to point. I like the wording better. Both have the same composition from point to point. Question 13. How do molecules of elements and molecules of compounds differ? In what ways are they similar? All right, now this is the definition of molecule in this text is that it has to be two or more atoms. So the molecules of elements and molecules of compounds differ in that the molecules of elements are made of the same, of one kind of atom, whereas molecules of compounds are made of different kinds of atoms. In what ways are they similar? They're similar in that they're made of two or more atoms. So let's look at the answer key. Molecules of elements contain only one type of atom. Molecules of compounds contain two or more types of atoms. They are similar in that both are comprised of two or more atoms chemically bonded together. All right, let's look at question 15. Many of the items you purchase are mixtures of pure compounds. Select 3 of these commercial products and prepare a list of ingredients that are pure compounds. Let's pick one of our favorites, Diet Coke. It's a mixture of pure compounds such as fructose and water. Water is a pure compound. How about beer? Beer has ethanol and let's see. Mixtures. Okay, so beer is a mixture. Diet Coke is a mixture. So I'm still thinking of food. Let me think of another thing that is a mixture. I'm having a hard time thinking of something else that is a mixture that isn't food. So, well then, I'm just going to pick root beer. It has, oh wait, did I say Diet Coke has fructose? No, it doesn't. It has aspartame. I'm sorry. It has aspartame. Root beer has fructose. Fructose in water. So apologies, I made a mistake there. So I'm glad I had a chance to correct it. So the answer key says answers will vary. So one sample answer, Gatorade contains water, sugar, dextrose, citric acid, salt, sodium chloride, monopotassium phosphate, and sucrose acetate isobutyrate. So let's go to question 17. Classify each of the following as an element, a compound, or a mixture. A, iron. Iron is an element. B, oxygen. Oxygen is an element. C, mercury oxide is a compound. D, pancake syrup. That's a mixture. E, carbon dioxide is a compound. F, a substance composed of molecules, each of which contains one hydrogen atom and one chlorine atom. I'd say that is a compound. Baking soda. Baking soda is a compound. I don't know off the top of my head what the formula is. We'll cheat later and go to the answer key. Baking powder, I know, is actually a mixture. So let's look this up. Iron is an element. Oxygen is an element. Mercury oxide is a compound. Pancake syrup is a mixture. E, carbon dioxide is a compound. F, a substance composed of molecules, each of which contains one hydrogen atom and one chlorine atom. Chlorine atom, that's a compound. G, baking soda is a compound. H, baking powder is a mixture. Oh, baking soda, the formula for baking soda is sodium bicarbonate. I should have known that. Baking powder, I'm just going to do a very quick Google here. Baking powder. Baking powder contains baking soda. It is a mixture of baking soda, cream of tartar, and sometimes cornstarch. Okay, so it is a mixture. There you have it. Question 19. How are the molecules in oxygen gas, the molecules in hydrogen gas, and water molecules similar? How do they differ? That's an odd question. How are the molecules in oxygen gas, the molecules in hydrogen gas, and the water molecules similar? Well, they have more than, the molecules have two or more atoms in them. That's about the only similarity I can point out. How do they differ? Oxygen gas and hydrogen gas are made of, oxygen gas is made of oxygen atoms, hydrogen gas made of hydrogen atoms, and water molecules are made of hydrogen, 2 hydrogen atoms and 1 oxygen atom. So 19, let's see what the answer key says. In each case, a molecule consists of 2 or more combined atoms. They differ in that the types of atoms change from one substance to the next. Well, I was more explicit than what they said, okay? Question 21. Prepare a list of principal chemicals consumed and produced during the operation of an automobile. Well, the principal chemicals consumed would be gasoline and oxygen, and that the thing that's produced is water and carbon dioxide. So let's look at the answer key. In each case, gasoline, a mixture of compounds, oxygen, and to a lesser extent, nitrogen are consumed. Carbon dioxide and water are the principal products. Carbon monoxide and nitrogen oxides are produced in lesser amounts. Now, that's not exactly the most fair question because this is drawing on kind of our own understanding of things. It's nothing in the text. So I have a problem with the fact that they threw that question in there. So that's more of just, that wouldn't be something that I think would be fair to grade. That's just my opinion. Question 23. When elemental iron corrodes, it combines with oxygen in the air to ultimately form red-brown iron 3 oxide called rust. If a shiny iron nail with an initial mass of 23.2 grams is weighed after being coated in a layer of rust, would you expect the mass to have increased, decreased, or remained the same? Explain. Okay, so if a shiny iron nail with a mass of 23.2 grams is weighed after being coated in a layer of rust, would you expect the mass to have increased, decreased, or remained the same? I would say the mass of the nail would increase because oxygen is combining with iron, and so that's adding more mass. If the mass of the iron nail increases to 24.1 grams, what mass of oxygen combined with the iron? So all I have to do is subtract 24.1 minus 23.2, and that is 0.9 grams. So let's look at the answer key. A, increased as it would have combined with oxygen in the air, thus increasing the amount of matter, therefore the mass. So the answer to B is 0.9 grams. What mass of oxygen combined with the iron? And it's 0.9. Okay. We can see here, this is a very long collection of questions. This is like, this lecture is like twice as long as the first lecture, and so is the homework exercise. So this is what it's like getting through college. It's not easy. Anyway, question 25. Yeast converts glucose to ethanol and carbon dioxide during anaerobic fermentation as depicted in the simple chemical equation here. So we have glucose, and that becomes ethanol plus carbon dioxide. A, if 200 grams of glucose is fully converted, what will be the total mass of ethanol and carbon dioxide produced? Going back to our law of conservation of mass, it should be 200 grams. So if we start with 200 grams here, the total mass over here should also be 200 grams. Oops. Conservation of mass. B, if the, let me just make sure I have that term correct. I don't want to I want to see if I have the word conservation of matter. I'm sorry, not conservation of mass. It's the conservation of matter. And let me just verify. The law of conservation of matter. Okay, so using the law of conservation of matter, we can answer that question. So if 200 grams of glucose is fully converted, what will be the total mass of ethanol and carbon dioxide? That means ethanol plus the weight of the mass of the ethanol plus the mass of carbon dioxide produced. It's 200 grams. The law of conservation of matter. Question B, if the fermentation is carried out in an open container, would you expect the mass of the container and contents after fermentation to be less than, greater than, or the same as the mass of the container and contents before fermentation? So the key here is an open container, an open container. So let's just think about this. If we're carrying out this fermentation and the glucose is turning to ethanol and carbon dioxide, but it's open, in an open container, that means the carbon dioxide is leaking out. So the mass, the mass after fermentation is going to be less than the mass of the container and contents after fermentation. That's contents inside the container, okay? And let's look at, I'm going to go to the answer key. It says here for question 25, the mass of the container and contents would decrease as carbon dioxide is a gaseous product and would leave the container. There you have it. So now, if 99.7 grams of carbon dioxide is produced, what is the mass of ethanol produced? I have a problem with this question. You're not going to have an easy time measuring the amount of the mass of carbon dioxide produced. You're going to have an easier time measuring the ethanol. So this is kind of a trick question, and I don't like that. But let's just deal with it as is. So we're supposed to have 200 grams here. So if 97.7 grams is carbon dioxide, you take 200. You take 200 for the ethanol, and I wish I need to try to, in the future, draw this so you could see it. You take 200 grams for the combined mass of ethanol plus carbon dioxide, and then you subtract 97.7. And that turns out to be 102.3 grams of ethanol. Like I said, that's more of a trick question because speaking in a laboratory context, you'd weigh the ethanol. But there are other problems. A little bit of the ethanol will evaporate. So, okay, well, I'm just going to let it go. I think it's more of a conceptual thing. So we went through all of the odd exercises. As I said, I can't vouch for my answers to the even exercises because I have nothing to corroborate it. So I'm just going to give it my best shot here. So question 10, how does a heterogeneous mixture differ from a homogeneous mixture? How are they similar? So a heterogeneous mixture differs from a homogeneous mixture in that every part of wherever you go in a homogeneous mixture, it's going to be the same. So like if you have Diet Coke, wherever you sample it from the bottle of Diet Coke, unless you're dealing with a carbonate. Let's do something simpler that doesn't have carbonation. Let's say we're dealing with Gatorade. If you sample Gatorade from any part of the bottle, it's going to be the same composition. Whereas a heterogeneous mixture, like say salad dressing, when you shake it up, depending on where you sample it, or even better, when you don't shake it up, depending on where you sample it in the bottle, you'll get a different composition. How are they similar? I'd say they're similar because they're mixtures. They're not a pure substance. 12, how does an element differ from a compound? How are they similar? An element differs from a compound in that only one kind of atom makes an element, whereas a compound has two or more kinds of atoms making it. They are similar in that they are pure substances. How does an atom differ from a molecule? A molecule is made of two or more atoms. An atom can, so a molecule can be decomposed into atoms. An atom is indivisible. In what ways are they similar? They have an atom in them. They're made of at least one atom. That's about the only thing I can think of. I think it's helpful to kind of try to conceptualize these things. 16, classify each of the following as an element, compound, or a mixture. I'd say copper is an element. Water, being H2O, is a compound. Nitrogen is an element. Sulfur is an element. Air is a mixture of things like nitrogen, oxygen, argon, carbon dioxide. Sucrose is a compound because it's made of, I should know this, hydrogen and carbon. I think oxygen. So we have to get to the carbohydrate chemistry. I'm embarrassing myself here. I should know this. G, a substance composed, actually that's going to annoy me a little bit. Let me look at the chemical formula of sucrose. I feel bad if I just let that go. Yeah, sucrose has oxygen in it. Sorry about that. I didn't want to let that go. A substance composed of molecules, each of which contains two iodine atoms. That is an element. Gasoline. Gasoline is a mixture. We learned that earlier. Now let me see. Let me go back and see what an element is. Element. Okay. I'm just looking at this. Matter can be classified into several categories. Mixtures and pure substances. Pure substances. Okay. The reason I'm doing this is sometimes the use of the word element isn't exactly the way that they're using it here. I'm just going to, in some scientific literature I've read, it doesn't use exactly the way that they're using it. At least that's the way I remember it. So let me just throw that caution out. Okay. 18, a sulfur atom and a sulfur molecule are not identical. What is the difference? Sulfur molecules are made of two or more sulfur atoms. A sulfur atom is made of only one sulfur atom. It's indivisible. 20, why are astronauts in space said to be weightless but not massless? Again, mass is an inherent property of matter. The weight is associated with the gravitation, the force generated by gravity on that mass. And that was discussed earlier in the text. I'm not going to belabor it. If you take physics, you'll see that question a lot. 22, matter is everywhere around us. Make a list by name of 15 different kinds of matter that you encounter every day. Your list should include and label at least one example of each, the following: a solid, a liquid, a gas, an element, a compound, a homogeneous mixture, a heterogeneous mixture, and a pure substance. I'm not going to go through all 15. Let's just do a few of them. A solid. Solid. A salt crystal is a solid. A liquid, water. A gas. A gas, let's say the oxygen in the air. It's very hard to find a pure gas. It's not, where there's not, it's not mixed with something. I can't think of anything in the house. I think I have propane somewhere, so I think that would count as a gas. An element. Can't think of any pure element. Diamond. Diamond is made of carbon. A compound. Water. A homogeneous, I know that was cheap. Homogeneous mixture would be, say something like cranberry juice. Heterogeneous mixture is salad dressing. And a pure substance, go back to water. As stated in the text, convincing examples that demonstrate the law of conservation of matter outside of the laboratory are few and far between. Indicate whether the mass would increase, decrease, or stay the same for the following scenarios where reactions take place. Exactly 1 pound of bread dough is placed in a baking tin. The dough is cooked in an oven at 350 degrees Fahrenheit, releasing a wonderful aroma of freshly baked bread during the cooking process. Is the mass of the baked loaf less than, greater than, or the same as the pound of original dough? It is less than, because the aroma means that some of this is going into the air. That's my guess. B, when magnesium burns in air, a white flaky ash of magnesium oxide is produced. Is the mass of the magnesium oxide less than, greater than, or the same as the original piece of magnesium? It is greater than, because the oxygen combines with the magnesium, so we're adding mass. C, Anton Lavoisier, the French scientist credited with first stating the law of conservation of matter, heated a mixture of tin and air in a sealed flask to produce tin oxide. Did the mass of the sealed flask and contents decrease, increase, or remain the same after heating? They remained the same. That's how he deduced the law of conservation of matter. And so that's it for all the exercises. This was quite a long lecture and homework session. I salute anyone who has stayed with me through all of this in a live lecture. This might be easier to do in a recorded format, so you can kind of take it in smaller pieces. So with that, that completes the homework exercises for section 1.2, the phases and classification of matter. Thank you for joining us today. And may the blessings of our Creator, the intelligent designer, the God and Father of our Lord and Savior, Jesus Christ, be with you.